we are going to graph rational functions without translations. So the four main components you need to find when graphing rational functions . Step 1, you need to find the horizontal asymptote and vertical asymptote. These are lines or imaginary lines, invisible lines, that these graphs will not cross or will not touch. They will get relatively close. Then you'll need to find the x-intercept and find the y-intercept. Okay, so find the x and y-intercept. Then you're going to graph and choose the x's to find more points. Now, when this last step, you can really get into depth of choosing your x's and getting a really precise graph. But as long as you have at least 2 points that will kind of show the angles or the curves of these graphs, they will be fine. Now, parent graphs, if we have 1 over x, our graph will essentially look like this, with horizontal and vertical asymptote at 0, and our base points will be 1, 1, and -1, -1. This would be here and here. If we have the function of 1 over x squared, we will have a graph that looks like this, with base points of 1, 1 and -1, 1, with horizontal and vertical asymptotes at 0 as well. So your graph will look similar to this. Sometimes your graph may have 2 horizontal asymptotes, or excuse me, vertical asymptotes, and it may have like a U in the middle, or a x to the 3rd power graph, with a combination of either this one left to right in the top hemisphere or the bottom hemisphere, or something along the lines of this one, here and here, or here and here. Okay, so with a middle partition, you will get something a little different. But as I said, you can choose the x's that you want, and you can find more points. So let's go ahead and graph some of these. Oh, I didn't tell you how to find the horizontal and vertical asymptotes. Vertical asymptote, it's just finding the domain. So set denominator equal to 0. And then your horizontal asymptote, you take the leading term of your numerator over the leading term of your denominator and reduce. If you have a number as a result, then that is the horizontal asymptote. If you have a x in the denominator, then y equals 0 will be your horizontal asymptote. If you have x in the numerator, or you're left with an x, then you have no horizontal asymptote. So I used this leading term reducing, instead of the powers, you actually are supposed to look at the degrees of your numerator and denominator. But I have found out that if you take your leading terms and reduce them, it's a lot easier to come up with your horizontal asymptote, especially if you have a number as a result. Then you can just move on instead of analyzing your degrees. So let's go ahead and graph this one. Okay, this one you could use translations, because it would be a stretch since we have a 4 in the numerator, and then we would actually move to the right 3 spaces on our 1 over x parent function. But let's go ahead and pretend, oh, we don't know how to use translations. So your vertical asymptote, you're going to set this equal to 0, the denominator equal to 0. So x equals 3. Horizontal asymptote, you get 4 over x, just your leading terms. 4 is leading, x is leading. Since x is in the denominator, y equals 0 will be your horizontal asymptote line. Then we need the y-intercept. Y-intercept is when you plug 0 in for x, and we get -4/3. Now, I don't like graphing fractions, but in this case, I lighten up a little bit because we are sketching. And then our x-intercept, you more or less set your function equal to 0. Well, you're going to multiply this denominator by 0, and you get 0 equals 4. Well, that's not going to happen. Or if you think about it, since you have a horizontal asymptote at y equals 0, that covers the whole x-axis. So of course you're not going to have any points on that axis, since we have a horizontal asymptote. So to graph, we have a vertical asymptote at 3. We have a vertical asymptote at 3, a horizontal asymptote at 0. And as you can tell, no point's going to lie on that x-axis. So you can skip finding the x-intercept if you have a line or a horizontal asymptote at y equals 0. Then we will plug in our y-intercept, which will be -4/3, which would be -1 1/3. And that's all the information we can place. So now what we're going to do is say, okay, what will happen if we have a value at 4 or 5? So here, let's 1, 2, 3. This is 4, this is 5, this is 6. So I'm going to go ahead and plug in the 4 for x, and we see that we get 4 as an output. Plug 5 in for x, we get 4 divided by 2, which is 2. And then we could do 6 as well, but then we'll get like a 4/3. So this will give me enough information to sketch my graph. Now on this side, we will explore 2. 4 over 2 minus 3. That's 4 over -1, which is -4. So at 2, when we plug in 2 for x, we will get an outcome of -4. Okay, and then we can sketch our graph, and that's what our graph will look like. And again, we could have just moved this whole graph over 3, or right to the 3, and then stretched it a bit. Let's look at a different one, a weirder one, if you may. So for the vertical asymptote, you are going to take your denominator and set it equal to 0. You can use the square root method, which you would add the 1 and then square root, or you can factor to solve this. So x equals plus and minus 1. So we'll have 2 vertical asymptotes. Your horizontal asymptote, we have x squared over x squared. Well, that reduces down to 1, so your horizontal asymptote is at 1. Next, we have our y-intercept. Plug 0 in for x, and you get a 4. So we'll have a 0, 4 point. And then for your x-intercept, just set the numerator equal to 0, because even if we have a denominator, we're going to multiply the denominator by 0, which would end up stating the numerator equals 0. You can factor, you can, however you need to solve. So we'll have 2 x-intercepts. So to graph this one's going to be a weird looking one, and I'm going to go ahead, let's see here, I was thinking about using the big guys as 1, but I'll go ahead and keep it as this. So we have a really skinny middle, and then we will have, let's see here, that's vertical asymptote. Then we'll have a horizontal asymptote at 2, or at 1, excuse me, at 1, and then we'll have 0, 4, 1, 2, 3, 4, and then we will have -2 and +2. Okay, so this doesn't look like much. You can plug in -1/2 and 1/2, but when you do that, you will get a negative value over a negative value, because this would be a fourth minus 4, and a fourth minus 1. Well, negative over a negative will give us a positive. So we'll be up here on our right and up here on the left. So this will give us a parabola in the middle, a very skinny parabola. And then for here, for these two regions, we know our answer is going to be down here somewhere, because we cannot cross these lines. So here's 2. So let's say at 3. Yeah, those are both at 2. So at 3, 3 squared is 9. And then all I'm doing is plugging in 3 in for x. So we get 5/8. So at 3 we're up here. So this will definitely be very skinny. And then the same thing here, if we plug in -3, -3 squared is 9. So we'll still get the same answer, which is really cool. I love squaring numbers because you get the positive value. So anyway, there is the graph of that. So the main point of graphing rational functions is finding your vertical asymptote, finding your horizontal asymptote, locate your x and y intercepts, and then plug that all in. Then to finalize your graph, you're going to choose whatever x you want that is not being barred by the asymptotes. You can pick whatever x you want, even halves or quarters, and then when you plug that in, you get your output, and then plug it into your graph, and then just kind of sketch it out. Okay, this will conclude this video.